the Taylor's formula says that if you have a function f of x, you can write it as a infinite polynomial. Infinite polynomial is probably not the right word, but you can write it as some infinite series, some power series is the word I should really be using. The sum from n equals 0 to infinity of the nth derivative of your function evaluated at a times x minus a to the n over n factorial. And sometimes people like to write this out kind of the long way, right? This is just f of a plus the first derivative evaluated at a times x minus a to the first, and so on, right? And actually, I'll point out a couple of things. F double prime of a times x minus a squared over 2 factorial. We'll write one more term. F double prime of a times x minus a cubed over 3 factorial, et cetera, forever and ever and ever. So, right, this is the, what's what I want to look at? Right, the Taylor polynomial or Taylor series for f of x centered at a, or about a is also language people use. And then I just want to point out, because I think this is kind of neat, the first two terms there, or the first degree per, or the product of the first degree, that's just the linearization. Right, that's the linearization of the function f about a, which we definitely learned back in 21a. Also known as just the equation of the tangent line to the function at a comma f of a. So sometimes people will talk about how the first couple terms of Taylor's formula are just linearization. There it is. So the point of writing this down is that I'm trying to point out that we want to avoid this whenever possible, meaning although you can certainly, and we will certainly use this formula some of the time, we try not to. Excuse me. And we specifically try not to by remembering a few things. So there are some series that I highly recommend memorizing the Taylor series for. Taylor series, usually the Maclaurin series, Maclaurin just meaning centered at 0. So these are all things you should definitely commit to memory. Usually in a normal setting, I would say you should commit these to memory because you wouldn't have just access to them. But depending on what your teacher's doing testing wise, you should recognize that these following things have series that are easily used. So 1 over 1 minus x is our bread and butter. It's the sum from n equals 0 to infinity of x to the n. And then 1 over 1 plus x is also, right? So really 1 over 1 minus anything is always up for grabs. So 1 over 1 minus, take your pick, right? That's going to be 1 plus your thing squared. It's going to be the sum from n equals 0 to infinity of your thing to the nth power. So maybe that's going to be minus x because you've got 1 over 1 plus x. Or maybe it's going to be minus x squared because you've got 1 over 1 plus x squared. Right? There's lots of things that can go in there. A couple actually things that go along with that are the natural log of x. Sorry, natural log of 1 plus x. So actually, we'll talk about natural log of x in a second. The natural log of 1 plus x. And yes, I know I said all these last class. I'm going to say them again because I think they're worth mention. This is the integral of 1 over 1 plus x. So it's the integral of 1 over 1 minus x. So if we were putting in a minus x and a minus x and a minus x, for example, then the integral of this is that. I know I've done it like 2 or 3 times already. I'm not going to actually I'm just going to say, if I actually write this one out specifically, It's negative 1 to the n times x to the n. If I integrate x to the n, I get x to the n plus 1 over n plus 1. So this ends up looking like x minus x squared over 2 plus x cubed over 3, which is just the sum from n equals 0 to infinity of, sorry, am I forgetting a term? Maybe, no. X to the n plus 1, n plus 1 times negative 1 to the n. Okay, a few more. Sorry, I know, sorry, I keep saying it, I've done this before. I'll just stop saying that. Keep doing it. You also have the arctangent of x. This one comes up a lot as the antiderivative of 1 over 1 plus x squared. So we've kind of got the same thing here, except instead of plugging in a negative x, we're plugging in a negative x squared. And so if you anti-differentiate that, you end up getting, right, so, pens, come on. This is 1. Be careful, James. The square is not outside of the parentheses there. Apologies. So this ends up being minus x squared plus x to the 4th. Right, because it's a minus x squared squared. And then when you have to differentiate that, you get the following. X minus x cubed over 3 plus x to the 5th over 5, etc. And so, right, there's lots of ways to write these. This one, the sum from n equals 0 to infinity. What have I got here? X to the 2n plus 1 over 2n plus 1 times negative 1 to the n. So this one and this one look very similar, which kind of makes sense because they're both looking like antiderivatives of 1 over 1 plus something. And then we've got sine and cosine, of course. Sine and cosine e to the x. So e to the x is the sum of x to the n over n factorial from n equals 0 to infinity. Sine of x is the odd powers. Sine of x is the sum from n equals 0 to infinity, the odd powers. So x to the 2n plus 1 over 2n plus 1 factorial times negative 1 to the n. And then cosine is the even powers. Sorry, I know I'm scrunching everything in here. Cosine of x is the sum from n equals 0 to infinity of x to the 2n over 2n factorial times negative 1 to the n. All right, so those are the ones I really think you kind of should know all of these. Let me write out e to the x, sine x, and cosine x just because there's a nice kind of connection to me. In fact, yeah, we might as well say this now. This seems like a good time as any. So e to the x, if you write it up a long way, is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, so on and so forth. Sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, so on and so forth. And cosine of x is the even power, so 1 plus x squared, sorry, minus, the cosine and the sine ones do alternate. One way you could think about this to remember that they alternate, if you, right, if they were all added together, that wouldn't really look like sine, right? Because if you added a bunch of polynomials, you just kind of get bigger and bigger and bigger. Whereas if you add, subtract, it kind of balances out, and so you can actually get the sine or cosine shape. Anyway, what you might notice, what I certainly noticed over the years, is that essentially e to the x is comprised of all the terms of sine and cosine. You take all the odd terms of e to the x and you get sine, except you have to alternate all the even terms of e to the x and you get cosine. There's actually a pretty famous thing, I guess theorem is probably the word I'm actually looking for, called Euler's identity. Euler spelled E-U-L-E-R. Right, everyone wants to pronounce this Euler. It's Euler. Doesn't really matter, but it is pronounced Euler. So Euler's identity is actually kind of cool. So I'm going to show you this just because it's very famous. You probably don't need to know this super a lot, but it only takes a minute. So I'm going to show it to you. So one thing you want to know. So after this, then we'll get back to our more regularly scheduled program. Can't remember what I is. The imaginary constant I is the square root of -1. And I squared is -1. And I cubed is -1 times the square root of -1, which is going to be negative square root of -1, or negative I. And then I to the fourth is equal to 1. And so then any higher power of I, you just cycle back around. So I to the fifth is I to the sixth is I squared, which is -1. I to the seventh is I cubed, which is -I. And I to the eighth is 1. So basically every fourth power of I, you get back to where you started. Okay, well, here's what we're going to do. We're going to write out e to the x, fill up myself more room. It's always the bane of my existence in my room here. Not enough room. Guess I'll erase these for a minute. So what we're going to do is we're going to write out, instead of e to the x, we're going to write e to the I times the theta. And yeah, theta because we are going to come up with a trig identity here. So if I write this out, I'm just replacing the x with the I theta. So we get 1 plus I times theta plus I times theta squared over 2 factorial plus I times theta cubed, right? It just goes on and on. Okay, but now let's use what we know about I. So this is going to be 1 plus I times theta. I squared is -1. So we're going to get minus theta squared over 2 factorial. I cubed is -I, so we're going to get minus I times theta cubed over 3 factorial. I to the fourth is 1. So we get theta to the fourth over 4 factorial. I to the fifth is just going to be I again. So we're going to get I times theta to the fifth over 5 factorial. Let me do like 2 or 3 more terms. I to the sixth will be I squared, which is -1. So we'll get minus theta to the sixth over 6 factorial. And I to the seventh will be -I. So we'll get minus I times theta to the seventh over 7 factorial. I think that's enough. Okay, so let's group all the i's together and all the not i's together. So let's see. The i's. Well, the i's are all the odd terms, which makes sense. Right? If you have I to an odd power, the even part of it will be negative or +1, and the leftover I will still hang around. So we're going to have, let's see, is this the way we usually write it? Yeah. So let's actually do the not i's first. So I've got 1 minus theta squared over 2 factorial plus theta to the fourth over 4 factorial minus theta to the sixth over 6 factorial. And so for the real part, the part that doesn't have an imaginary coefficient, that's just cosine, right? That is the Taylor Polynomial, the Maclaurin Series for cosine. And then if we group all the I ones, which are all the odd ones, they also alternate. So I can factor out an I and say this is going to be theta minus theta cubed over 3 factorial plus theta to the fifth over 5 factorial minus theta to the seventh over 7 factorial, etc. Well, this is nothing other than cosine of theta plus I times sine of theta. So this is a pretty famous equation. What is identity? And you might be more familiar with it with the specific equation e to the I pi equals, I think we'll use right as 0 minus 1 to be extra special. To have 5 of the most important numbers in the world all in one equation, e to the I pi equals 0 minus 1. It's exactly because of this equation. E to the I pi is going to be cosine of pi, which is -1, plus I times sine of pi, which is 0. Kind of neat. Also pretty important. Like this equation definitely comes up a heck of a lot. Some people will actually write this. I think the better way to write this is e to the I pi plus 1 equals 0. That's a nicer way of writing it. But this is certainly kind of cool. Comes up in various places in future math classes. So if you're taking more math classes later on, this will probably pop back up at some point. But it's also nice it's a nice way of actually kind of remembering that the Taylor series for e to the x definitely has the pieces for sine and cosine in it. Why is the I'm assuming that's an I, Mariah? Yeah. Why is the I turned into 1? So where? Sorry.
I'll unmute myself. So you have the cosine theta plus I sine theta, and then you end up with, or sorry, for the EI pi, you equal 0 minus 1. So where does that 1 come from?
So this is kind of, so here's what it really is. If I actually write the equation here, e to the I pi equals cosine, so I'm just plugging in pi for theta. So it's equal to cosine of pi plus I times sine of pi. But cosine of pi is -1 and sine of pi is 0. So this just ends up being -1 plus I times 0, which is just -1. And then people do dumb things like write it like this, so you have the 0 in there as well.
Got it.
But this is just purely manufactured. Right. It's really the equation is e to the I pi equals -1. Okay, so don't worry too much about this. It's just an interesting thing that does like come up in other places, but it's not super duper important for class today. No, let me do other. Oh, that's kind of neat. Okay. Anyway, back to more Taylor and Maclaurin series stuff. So yeah, let's go ahead and talk about that. Yeah, let's go ahead and work through some of these. So I'm looking at problem solving number 6. Yeah. So we've already got e to the x and sine of x. Let's go ahead. So I should point out, not every series is centered around 0. For example, we could find a Taylor series for f of x equal to the natural log of x, not natural log of 1 plus x, but natural log of x, centered, well, you can't center it at 0 because it's undefined there, centered at maybe a equal to 1. So 2 ways you can do this. The hard way, taking all the derivatives, maybe we'll do that, or the easier way, trying to write natural log using other series that we know. So here's what I'm going to do. I'm going to say that the natural log of x is equal to the integral of 1 over x. And then I can write 1 over x as 1 over 1 minus something. Okay, what has to go in the parentheses here so that this is still equal to that? -1 is almost part of it. So really, I'm just asking this question. I'm just phrasing it in the dumbest way possible. I need x to equal 1 minus the parentheses. So I could solve for the parentheses, right? I could be like, okay, add the parentheses and subtract x. Oh, that's what needs to go in there. Right, I kind of said it the most roundabout way possible. We're just trying to figure out what does this have to be so that x equals 1 minus this. So this is, 1 minus x. And that checks out. 1 minus x is just x. And then we can use the geometric series thing we know about 1 over 1 minus r. Right? This is the integral of 1 over, I'm literally about to write the same thing down. 1 over 1 minus r, right? That's going to be 1 plus r squared plus r cubed. Right? That's what we've got. This is probably not the easiest thing to integrate. Right? I don't want to integrate this piece by piece. So this is where it really does pay to actually write this as an infinite series. This is equal to the integral of the series 1 minus x to the n equal to 0 to infinity. Okay. I don't love integrating 1 minus x, or really minus x at all, because minus x to the n, technically I need to do a u sub. The easy way around this is to factor out the negative 1 to the n. So 1 minus x to the n power is the same as negative 1 to the n times x minus 1 to the n. You guys cool with that? Right, if you multiply these together, the negative 1 distributes and you get negative x plus 1 to the n, negative x plus 1 to the n. Hopefully everyone's cool with that. I always do that, right? If I know I have to anti-differentiate or differentiate a series and there's a negative x, I'm going to pull out that negative 1 to the n so I don't have to deal with that. Because this is just a constant as far as x is concerned. So I can integrate this. This is going to be the series from n equals 0 to infinity of negative 1 to the n times the antiderivative of something to the nth power is going to be x minus 1 to the n plus 1 over n plus 1. So cool. Also, look, it's centered at 1. How about that? So here's what we get. We get that the natural log of x is equal to the sum from n equals 0 to infinity of x minus 1 to the n plus 1 over n plus 1 times 1 to the n. Couple things to mention here. Quite a few things, actually. The first thing is that I didn't lie. I'm not a liar. But I kind of left something off that's kind of important. When you integrate something like this, there's a plus c. 9 times out of 10 is probably a low estimate, probably like 99 times out of 100. This c is going to be 0. But we do have to at least think about checking what it is. How do we check? Well, where do we know a series has to converge, right? This series might converge almost nowhere. The radius of convergence could be 0, but the series always converges at its center. The center here is 1. So I'm going to plug in 1 to both sides. If I plug in 1 here, what's the natural log of 1? 0. 0, 0. Sorry. My wife told me the other day I did this. I'm like 0. She's like, it's like a white supremacy symbol or something. I do not mean it that way at all. I apologize if I've accidentally made some dumb symbol ever. I'm like, okay, that's a symbol I've made all my life. So sorry if that's something that is known to be something else. I wasn't aware of that. 0. I'll just say 0. Anyway, not to be an idiot, but trying not to be an idiot. Yes. So yeah, maybe I'll delete that part from the video later. Probably not. I don't really care that much. I mean, I care. She's like, wow, he's getting off on a huge tangent. Let's talk about tangent. All right. So anyway, we plug in 1 here. Natural log of 1 is 0. You plug in 1 here. All the terms are 0, right? We get, and when you plug in 1. If n is 0, x minus 1 is 1 minus 1 to the first power is going to be 0. 0, 0, 0. So all these terms are 0. So 0 equals 0 plus c. C has to be 0. And this is what happens most of the time. This value here is essentially going to be whatever this is when you plug in the center. because all these parts are just going to go away to 0. Occasionally you get something else. I know someone else, there was actually one problem that someone else was doing the other day. I think it was x plus 1 times the natural log of x plus 1, where we got something slightly different, but most of the time we just get 0. The other thing we should talk about is, where does this converge? We know that the center is 1. And actually, we know that the radius is also 1 because it came from this kind of thing. And a geometric series, which this is, right? This here is a geometric series. A geometric series has a radius that converges that's 1, or I should say your R value has to be less than 1 in absolute value. And then when you integrate or differentiate, that doesn't change the value of the radius. The only thing that does change is the endpoints. So our center is 1. Our radius is also 1. So our interval of convergence is x is between 0 and 2. But does it converge at the endpoints? Well, it shouldn't converge at 0 because it's undefined at 0. And if you plug in 0, it's actually not convergent. I hate erasing stuff. That's part of the problem, but oh well. So if you plug in x equal to, so we're checking the endpoints, right? You plug in 0, you get the sum of -1 to the n plus 1 times -1 to the n over n plus 1. This is not alternating because -1 to the n plus 1 times -1 to the n is -1 to the 2n plus 1, which is always -1. And -1 over n plus 1 diverges, right? It's the harmonic series essentially. So this is divergent, whereas if x is equal to 2, then you're going to get the sum of 2 minus 1, which is 1, 1 to any power is 1, -1 to the n over n plus 1. This is convergent by the alternating series test. So there is my interval of convergence. It's 0 exclusive. Come on. To 2 inclusive. Okay. But the bigger story I'm trying to tell here, and I feel like I'm doing not a great job of it today, is that we're going to use known series whenever we can to find other Taylor or Maclaurin series that we're asked about. So some examples. What's the Taylor series for sine of x squared? I should say Maclaurin because it's sine is 0. So Maclaurin series. Well, that's really not terrible if we remember what the Taylor series, the Maclaurin series is for sine of x. We know that sine of x is the odd powers alternating over the same odd number factorial. I think it's easier to write up the series in the compact, like sigma notation. So it's the sum from n equals 0 to infinity, odd powers. So we need x to the 2n plus 1 over 2n plus 1 factorial. And then we need to alternate starting with a positive term. So we need a -1 to the n. And people usually write that in front, but I always forget it until the end. It doesn't really matter where it goes. So that's sine of x. Sine of x squared is super not terrible. We just substitute x squared for x. So it's x squared to the 2n plus 1 over 2n plus 1 factorial times -1 to the n. That's literally it. The only other thing you might do with this is then, say x squared to the 2n plus 1 is x to the 4n plus 2. And you started writing out terms. So you could actually plug in 0, right? So if you plug in 0, you get x squared over 1 factorial, which I'm not going to write the 1 factorial because that's silly. Then n equals 1, you get minus, let's see, x to the 6th over 3 factorial plus x to the 10th over 5 factorial. right? It's the same as the sine Maclaurin series, except all of your x's, the power doubled, because literally the power doubled when you plugged in x squared for x. So this is what I mean when I say we want to try and make it easy. I don't want to do the whole long finding all the derivatives of all the things, right? We could, but it's terrible. Although sometimes we have to. Let's look at this next one. Sure. What if I wanted to find, actually, let's look at a couple more examples of this. So similarly, sine of x over x. We don't want to do this the long way. And I don't remember if everyone was here for the last, but when I say the long way, I mean the following. You find all these derivatives, right? So again, let's say Maclaurin. Yeah, I guess that's fine. Here it feels weird to center this around 0 because technically it's undefined at 0, but it's not a huge deal. Right, so the long way here is to find f of 0 and f prime of 0 and f double prime of 0 and all that, and try and find a pattern for it. The problem is it's a giant pain once you have a function that's even a little bit different than the original. Here I'm going to have to use the quotient rule, right? F of 0, okay, f of 0 doesn't exist. F prime of 0 is going to be bottom through the top minus top through the bottom, all of the bottom squared. Things are looking bad. First of all, because things aren't even defined very nicely. But second of all, because the next derivative is going to be even worse. The next derivative is going to be worse. The whole idea here is, again, to say, well, that's just 1 over x times sine of x. And sine of x is right, it's just that. And then be like, oh yeah, just multiply 1 over x by everything. So you get 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus x to the 6th over 7 factorial, which is kind of cool. I feel like I'm probably glossing over something here about where this is really defined, because we know the sine of 0 over 0. We know its limit is equal to 1, but we know the sine of 0 over 0 technically is undefined. So yeah, that seems slightly dicey. I will, by the way, I'll fully admit, this section of math is not my strongest suit. Like, I'm fine explaining the tests for convergence, divergence, all that stuff. But when we start getting into the Taylor series stuff specifically, I will admittedly get a little shaky on things. Certainly I can use the textbook and look things up, but sometimes I'm kind of like, oh, well, yeah. What does the remainder term tell you? Okay, good. That's Julian. Excellent lead in. That's just where I was going here. So, yeah. Let's talk about the remainder stuff. So let me hit you with this question. Yeah, here's a good question that kind of gets at that. How do I want to, let's see, actually. I think I have a different one. I think it's a little bit. Sorry, yeah. Let's actually let me give you kind of the big picture, and then we'll get down to an example. So here's the stuff about Taylor's remainder theorem. Taylor's remainder theorem says the following. Actually, well, I'm gonna get back to Taylor's remainder theorem, but I want to say something else first. So if we have a decreasing alternating series, the one that like converges by the alternating series test, the error is always bounded by the next term. So, right, if you're writing your series, sorry, there's always like there's just so much involved here. So the Rn, which is the remainder after n terms, is less than or equal to the absolute value of an plus 1. Right, this is where we've got, like your series is A1 plus A2 plus A3 plus, I guess it's alternating. It's A1 minus A2 plus A3 minus A4 up to some, right, AN term. The first n terms, that's called your nth partial sum. And then the step after that, that's your Rn. And what the alternating error bound says is that if it's an alternating series, then this error, all of those terms after the first n terms added together, it's going to be less than or equal to just whatever the first part of that is. It's kind of neat. So for example, one of these alternating ones we've been looking at, like sine, right? We know that sine of x for the third time is x minus x cubed over 3 factorial plus x to the fifth 5 factorial, etc. So we can say that we know that sine of 1, for example, well, it's approximately, if I just use, let's say I use the first 3 terms. Sine of 1 is 1 minus 1 over 3 factorial plus 1 over 5 factorial. And if you add those together, you're going to get, I have to add fractions. 120 over 120 minus 20 over 120 plus 1 over 120. That's going to be 101 over 120. But what we can say is we know that this is not exactly right, but we can be certainly sure that the error, so I would say R5, right? Because I know I'm not adding up the first 5 terms, but I'm stopping at the 5th degree term. So this is really R5. R5 is going to be less than or equal to the next term, which would be the absolute value of 1 over 7 factorial, which is equal to 1 over, what's 7 factorial? It is something. I used to know it. 720 times 7, 4,900 plus 740, 5,040. So our error is less than 1,540. Less than 1 over 5,040. I feel like I said the wrong words there. Okay. So the problem with this, as you might have noticed, is only is true for an alternating series. So what if we have something that's not alternating? Well, this is where the Taylor's remainder theorem comes in. It's a little wordy, but here's the gist of it. Taylor's remainder theorem says that we can estimate the error. So the error after the first n term, so the error of the remainder is less than or equal to the absolute value of the n plus 1 derivative at some z, we'll talk about where z lives in a second, times x minus a to the n plus 1, where a is the center, divided by n plus 1 factorial. Where a is the center and z is between x and a. The reason we say between is because it's not always clear what, like sometimes x is larger than a, sometimes x is smaller than a, depending on where you're evaluating that. So we just say z is between x and a. And yeah. Yeah. And yeah, specifically, so a is the center, z is between a and x, and it's also the place where the n plus 1 derivative is maximized. So z is between a and x, and f of n plus the n plus 1 derivative at z is as large as possible. So sometimes what people actually end up writing is that this is equal to m times x minus a to the n plus 1 over n plus 1 factorial, where m is bigger than or equal to the n plus 1 derivative of z. And capital M can be a little wavy. Oftentimes we make this bigger than it actually has to be because it's just easier to. So let's look at an example. I want to, let's see how we're going to do this here. So let's use a third degree Taylor polynomial to approximate e to the, that's not very exciting, e to the 1, fine. We know what e is approximately, whatever, still a good example. And also bound the error. Okay, so we're gonna pick e to the x. We're gonna use the Maclaurin series, set it to 0. So we know that e to the x is, I'm gonna say approximately because I'm only using a finite number of terms. It's gonna be 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Right, that is my third degree Taylor polynomial set to 0, or my third degree Maclaurin series for this function. So then we can say that e to the 1 is approximately 1 plus 1 plus 1/2 plus 1/6, which is going to be, let's see, 2.5 plus, I'm using a decimal, which I wouldn't normally, but because we know what e is already approximately, 1/6 is 0.1666, etc. So this is going to be 2.66 forever, which is not bad, right? We know e is like 2.71-ish. But we can also use this to then bound the error. So the error, Rn, is less than or equal to the n plus 1 derivative. Nice thing about e is it's always its own derivative. So the function is e to the x. The first derivative is e to the x. The fourth derivative is e to the x. So we're looking at R3, which is going to be the fourth derivative at z times x minus the center to the nth power, which is 4, all over 4 factorial. So that's going to be our error bound. And so the only thing, so this always gets to be like, so just like, wow. Our x value is what we're plugging in for x here. So this should actually be a 1. So what we've got is 1 over 4 factorial. And then we have to figure out what's the bound on e to the x. Well, this is where things get kind of self-referential. The fourth derivative is e to the x. So the fourth derivative at z is e to the z. So what's the biggest this can be? Well, where does z have to live? This problem, z lives between 0 and 1 because the center is 0 and x is 1. So in this problem, the biggest e to the z can be is e, which seems kind of dumb to use e in our approximation of the error that we're getting as an approximation of how close we are to e. If we knew what e was already, we would just kind of say, so often this one we say, well, this could be no larger than e, so let's make it 3, because we know that's for sure going to be a good upper bound. So you're always trying to pick something bigger than what you've actually got. So this is going to be sorry, I forgot the time, which is definitely going to be less than 3 over 4 factorial, which is 3 over 24, which is 1/8. So we are absolutely certain that our estimate is within 0.125 of the actual value, which it is. So that's one example of saying, here's a Taylor polynomial that's approximating a polynomial. We're using it to approximate an actual value of a thing. And then we're going to kind of say our error is about this much. Let's do this for a different value here, because there's a kind of I think, a nicer example. One that we don't know as well. So what if I wanted to do the same thing, but now I wanted to approximate e to the negative 1? Well, I'm going to use the same information, right? I'm going to do 1 minus, so I'm just plugging in negative 1 instead of 1. So I'm going to get 1 minus 1/2 plus 1/6, right? That's going to be, sorry, oh, I forgot a term. Ooh. Whew. Oh, man, terrible. Maybe I should just write the whole thing out instead. Let's do that. So I'm going to do e to the negative 1. It's going to be approximately 1 plus negative 1 plus 1/2 plus negative 1 over 6. Those cancel. 1/2 minus 1/6 is 3/6 minus 1/6, which is 2/6, which is 1/3. So e to the negative 1 is about 1/3. How good is our estimate, or how big can our error be? Well, now, again, our error, I don't want absolute values. No, not really. Our error is less than or equal to, again, the fourth derivative at z. So that's going to be e to the z x minus a to the 4th power over 4 factorial. The difference here is that now z is between 0 and negative 1, which I should have written 0 on the other side. And if we want to pick the z that's going to make e to the z as big as possible, we're going to pick 0 here. So e to the z is definitely less than or equal to 1. This is less than or equal to 1 times negative 1 to the 4th is also 1 over 4 factorial. Less than or equal to 1 over 24. Not too shabby. So that means this e to the negative 1 is approximately 0.333 forever and ever and ever. And our error is less than or equal to 1/24, which is, if you want a decimal approximation of that, it is some number that I knew once upon a time. 0.0416, I believe. Now I'm going to have to check that because I can't not. Let's see. 1 divided by 24. Yeah. Good job, James. I got it right. Anyway. So we know that e to the negative 1 is this with this much error at the most. So it can be like as much as 0.344 or as small as 0.28 something. Cool. I always say e to the negative 1 is about 0.3. Okay. So the other thing we can do, so there's usually kind of two styles of error questions. There's either, for this approximation, what is the most the error could be, or how many terms do we need in our approximation so that the error is less than some threshold. Let's look at some examples. Let's see. Yeah. That's a weird question. And I'm looking at this example I've got. I'm like, that's kind of neither of those things. It's all right. I don't want to do that one though. Let me see here. E to the, sure thing. So the way I got e to the z, so this error formula, So the error after you add the first n terms together is less than or equal to the absolute value of the n plus 1 derivative evaluated at z times x minus a to the n plus 1 over n plus 1. By the way, this is essentially the next term in your Taylor polynomial, right? So let me actually, I'm going to say a few more words here. If we start writing out the Taylor polynomial, right? So, sorry, all this stuff, I find this stuff taxing for my brain. Not that I'm not going to do it. I'm just telling you, like, I have to like think more. So our Taylor polynomial centered at A is 1 plus x minus a plus. Oh my gosh, sorry. I already forgot my brain. Come on, brain, you can work. I forgot the f prime of a. And it's not 1. Holy smokes. Let's try this again. Okay, brain, work this time. Okay, brain's working. All right, we get these terms, and we keep going. So we get to the nth term, which is going to be the nth derivative at a times x minus a to the n over n factorial. And then the next term, I need more room. Sorry, so the next term is the n plus 1 derivative at a times x minus a to the n plus 1 over n plus 1 factorial plus more stuff. So here's the deal. That's your Sn, your nth partial sum. And we're asking, how close is this nth partial sum to the actual thing, f of x? Well, this is how much we're off by. So all this out here, right now I know I've only written one term, but it's right, it's this plus all the terms after it. So this is your remainder after the first n terms. And what we're saying is the remainder is less than or equal to this. Now I want to point out, this is not the same as the next term. It's close, but the difference is the next term is the n plus 1 derivative evaluated at a, the center, times x minus a to the n plus 1 over n plus 1 factorial. Whereas this is the n plus 1 derivative evaluated at z, where z is between x and a. We don't never know what z is. Z is just some number in between x and a, and our job is always to figure out what should z be to make this as big as possible so that we can get an upper bound for the error. Right? We're never actually finding the exact error. We're just saying the error is less than or equal to something. So to answer your question, how did I get e to the z? Well, I found the n plus 1 derivative. But e to the x, the first derivative is e to the x. The second derivative is e to the x. The third derivative is e to the x. And the one I was interested in, the fourth derivative, was e to the x. But then I'm using z instead of x because I'm trying to find the value that makes it the biggest. So my fourth derivative at z was e to the z. And then I said, okay, what's going to make this the biggest? Well, here in this example, a is -1, x is 0. I got that backwards, sorry. A is 0, x is -1. So z has to be between -1 and 0. And in this example, 0 is going to be what makes it the biggest. E to the 0 is 1. So that's why I have a 1 here, right? That's my e to the 0. Hopefully that clarifies what's happening there. More generally, we're trying to just figure out how to bound this. That's usually the hardest job of these questions, is how do we bound that n plus 1. Z is always the value that's going to make that derivative as large as possible. Usually, it's either the right or the left endpoint. For an increasing function like e to the x, it's the right endpoint. For a decreasing function, it's at the left endpoint. But for other things, you're just going to have to guess. And I can give you guys an example of that. Sure. So let's see what I've got here. So yeah, so let's do this next one. Sure. I got time. Yeah. I'm gonna leave that there. So what if I wanted to estimate? Sorry, these problems always get kind of just super funky. Where'd you go? Sorry. Cool. Gosh, sorry, my brain is turned off. Sure. Let's estimate sine of 18 degrees using the first three non-zero terms of the Maclaurin series. And let me grab one thing here. So before we can do this, we have to change it to radians. So 18 degrees times pi over 180 degrees is pi over 10 radians. So we're estimating sine of pi over 10. I'm using the first three terms, the first three non-zero terms, and we know that sine of x is, again, it's the odd ones. So it's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. I want to point out, if someone says the first three non-zero terms versus the third degree, right here, the third degree Taylor polynomial would just be x minus x cubed over 3 factorial, because that's where you end the third degree. So this would be approximately pi over 10 minus pi over 10 cubed over 3 factorial plus pi over 10 to the 5th or 5 factorial. No one wants to actually figure out what that is. Now, here's the thing, and this is, so I will say people often, what's the word I'm looking for? We often try to kind of get out of doing anything too terrible. And this is alternating. So instead of finding the whatever derivative and using the Taylor remainder estimation theorem, we'll be like, oh, it's alternating. Alternating series, the remainder are, what would it be? I guess R, like R, I think it's R5. And no, it's probably R3. It's always kind of weird when you have things that skip terms. So R3 is less than or equal to the next term, which is going to be pi over 10 to the 7th over 7 factorial. So whatever this estimate is, it is definitely within this much of the actual value of sine of pi over 10, which is interesting because it's alternating. Right. Let's see if I can grab another example that's a little more interesting. Whew. Sure. Yeah, let's go ahead and look at, I guess there's one more series I should talk about before we can, because there's some examples I want to do, but we're missing one series, which is kind of important, which is also kind of a pain in the ass. But yeah, there's one more specific series we should talk about, which doesn't have a nice, well, I mean, it has a, you could say nice formula, but that would be feel like I'd be abusing the word nice by saying this. So let's look at the binomial series. And this is definitely, so this is in your textbook. I probably would not recommend memorizing this one, but recognizing when you have something like this so that you can just look it up in the textbook. So I want to find the Maclaurin series, meaning centered at 0, for f of x equal to 1 plus x to any power p. P can be positive, p can be negative. You got a power. So here's what I know. I know that the Maclaurin series is the usual kind of deal, right? It's f of 0 plus f prime of 0 times x over 1 factorial, which I shouldn't write. Whoops. Come on. Plus f double prime of 0 times x minus 0 squared over 2 factorial plus f triple prime of 0 times x cubed over 3 factorial, et cetera, et cetera, et cetera. So we need to find the f of zeros, the f prime of 0, et cetera. So f of 0 is just 1, right? 1 plus 0 to the pth power is going to be 1. I guess I should write down my functions too. Let's take the derivative. So f prime of x is p times 1 plus x to the p minus 1, which is using the power rule. So if I plug in 0, f prime of 0 is going to be p times 1. And then f double prime of x, I'm going to take the next derivative, so I'm going to get p times p minus 1 times 1 plus x to the n. I might have solved this as awful. It doesn't seem quite as awful as I made it out to be. The second derivative at 0 is p times p minus 1. And it just kind of keeps going in this way, right? The third derivative is p times p minus 1 times p minus 2 times 1 plus x to the p minus 3. So the third derivative is going to be p times p minus 1 times p minus 2. And it kind of just keeps going this way. So we can write out the Maclaurin series for this as the following, which I'm going to have to write it on the other side of the board. So 1 plus x to the pth power is equal to f of 0, which is 1, plus f prime of 0, which is p times x, plus f double prime of 0, which is p times p minus 1 over 2 factorial times x squared. The next one is p times p minus 1 times p minus 2 over 3 factorial times x cubed. And it just kind of goes on like that. You can write this as like a series. It kind of looks gross, but you write it as the sum from n equals 0 to infinity of n factorial on the bottom, x to the n on top. Sorry, yeah, over there. And then up here you have, right, so if you basically go all the way till you get to p minus n. So you have p times p minus 1 times p minus 2 all the way to p minus n. All right, double check. I feel like I might have, I think that's maybe slightly wrong, because if n is 0, you don't get p times x to the 0. I think what we have to do is we have to adjust for the first term and do it like that. So when n equals 1, you get p. I feel like I've done this stupidly somehow. I don't know. Now I feel like let me look up the formula just so I don't make it really dumb. Sorry, you've got dumb James today. Smart James didn't show up. I think I have written it correctly. How about that? They definitely use different notes. Oh no, I'm off by 1. Okay. Cool. Yeah. This should be down to p minus n plus 1. Which makes, that makes sense, right? Because if n is 3, I should get down to p minus 3 plus 1, which is p minus 2. Seems good. But again, I wouldn't memorize this. If you're familiar with the choose function, which if you've ever taken a stats or a probability class, you might be, you can write this as 1 plus the sum from n equals 1 to infinity of p choose n times x to the n. This is just that. If this doesn't look familiar to you, don't sweat it. You don't need to worry about it. But if this does, it's kind of a simpler way of writing it. Okay, so what this means is you can write out all kinds of stuff that was kind of terrible before. Like, so I'll remind you guys, previously, we did the Maclaurin series for like the square root of x, and it was kind of gross. But now you can do the Maclaurin series for basically 1 plus x to any power. So I guess we did, okay, fine. So for example, if I wanted to find the Maclaurin series for, I don't know, 1 plus x to the, what have I got here? The square root of 1 plus x, for example, instead of finding all the derivatives and then trying to find a pattern, you can say, well, it's going to be this. It's going to be, well, my power is 1/2. So it's 1 plus 1/2 times x plus 1/2 times negative 1/2 over 2 factorial times x squared. It just kind of goes on this way. The words. Let me give you guys one more example that might be somewhat redeeming, and then we will call it a day. So why might you care about something like this? Well, actually, I think I've got 2 examples. We might sometimes want to estimate integrals that we can't actually integrate. For example, where'd you go, example? I just had you. Sorry, I've lost it again. Like, yeah, you have, you crazy man. No, I'm just kidding. Yeah, I just can't seem to read anything here. Sorry, let me grab my example notes over here. Yeah, so what if I wanted to estimate, holy smokes. I actually had an example that was somewhere on here that I was like, that's a great example, and now it's disappeared. Sorry. It was an example I really wanted to do. And now it's gone. Oh my God, internet, I don't care about GameStop. Stop trying to tell me about GameStop. Okay, well, I'll just do this other example. Yeah. So I want to estimate the integral of x squared over 1 plus x to the 4. From 0 to 1. Using the first 3 terms of a power series. So this looks geometric to me. I'm going to say that x squared over 1 plus x to the 4th is equal to x squared times 1 over 1 minus negative x. Negative x to the 4th. So it looks geometric. So this is looking like x squared times, this is 1 over 1 minus r, so this is 1 plus r squared, etc. So this is looking like x squared times 1 is x squared minus x to the 6th plus x to the 10th, and so on. But I only use the first three terms, so that's all I need. So I can say that this integral, x squared over 1 plus x to the 4th, is approximately the integral from 0 to 1 of x squared minus x to the 6th plus x to the 10th, which is going to be x cubed over 3 minus x to the 7th over 7 plus x to the 11th over 11 from 0 to 1, which is going to be 1/3 minus 1/7 plus 1/11. That's our approximation. We also are curious about the error. So sorry. So how do you know what the error is? Well, it's going to feel like cheating, but it's an alternating series. An alternating series is always, the error is always bounded by the next term. So really, not everything's alternating, which I was trying to give you an example of and lost it. But if you see something that is alternating, you're kind of in luck. If you're talking about error, the error is always just going to be less than whatever the next term would be. So the next term of this alternating series would be 1 over 15, negative 1 over 15. Right? If I actually wrote the next term, and this would be, the next term would be negative x to the 4th cubed, which would be x to the 12th times x squared, which would be x to the 14th. And then anti-differentiating that, x to the 15th over 15. So the error is less than 1/15. Great. I actually wanted to get the other example I had for you, which I really actually had and completely just, my brain farted and I lost it. Okay, well, let's look at this one. Oh, there it is. I found it. Sorry. Okay. Here's the one I actually wanted to ask. Sorry, it's just hard to read small time. I think I'm just getting old and I can't read small time anymore. I want to estimate the integral from 0 to 1 of x e to the negative x cubed dx, which definitely cannot be integrated. And here I want the error to be less than 0.01. Right? Right. Okay, so same idea. We're going to write this as a power series or a Maclaurin series. E to the negative x cubed is going to be the power series for e to the x, which is with a negative x cubed in place. So we're going to get, now the problem here is you might already be seeing that this one's going to be alternating as well, which isn't as exciting as it could be. So this is going to look like, right, we know e to the x is 1 plus x squared over 2 factorial. This is going to be 1 plus negative x cubed. Come on. Plus negative x cubed over 2 factorial. Sorry, negative x squared over 2 factorial. All right, so, and then we're going to multiply that by x. So here's what we've got. We got the integral from 0 to 1 of this whole thing. That's looking like x minus x to the 4th plus, let's see, x to the 6th times x to the 7th over 2 factorial. So it's like my power is increasing by 3 every time. So then minus x to the 10th, 3 factorial. So the problem is, how do I know how to bound the error here? Like, how do I know how many terms I need to use to bound the error? Well, let's see here. Sorry, one sec. So let's go ahead and write out. So if we start integrating this thing, right, we're going to get. So if we integrate this, we know the powers are going to increase by 1. We divide by the new power, and we plug in 1 and 0, which are very convenient limits of integration. The 1's just going to give us all the coefficients, and the 0 is going to give us nothing. So when I integrate this, right, this is going to be x squared over 2, which is just going to give me a 1/2. This is going to be x to the 5th over 5, which is going to give me a 1/5. This is going to be x to the 8th over 8 times 2 factorial. So it's going to be 1 over 8 times 2 factorial. Plus, not minus. This is going to be 1 over 11 times 3 factorial. And then the net, right, it's just going to keep going, right? So you're going to just keep getting a 5 times 1 factorial, and 8 times 2 factorial, 11 times 3 factorial, 14 times 4 factorial. The next one would be 17 times 5 factorial. So the question is, when do we get to a place where the remainder is less than 0.01 or the error is less than 0.01? Well, it's alternating. So we just have to get to a place where the next term is less than 1/100th. It's not this one, right? It's not this one. That's 11 times 6. This one's definitely big enough. So this is the last term we need. So we don't need this. We need all of these. So whatever this would be, this approximation has an error that's certainly less than 0.01 because the error is definitely less than 1 over 14 times 24, which is smaller than 1 over 100. So our error, our R4, is less than 1 over 14 times 4 factorial, which is definitely less than 0.01.